I think I will stop with the numerical solvers, of solvers of numerical, of nonlinear equations. So there are, we passed through several methods, so you have idea how they work, and there are some methods we didn't touch, which you can take a look in the book, but anyway, I hope you catch the idea. So we go to the second topic, which is also very basic, is numerical linear algebra. So here I suppose that you know something about linear algebra, and if you don't, that book we're using, it has rather detailed introduction to all concepts you need. So if you don't remember, just take a look. And I will just pass very briefly about basic concepts, mostly definitions. So in linear algebra, we work with vectors. And we will be working with vectors which is usually written as collection of numbers, right, from 1 to n. And it's, by default, it's column. It's either n-dimensional or, and it either has real components or complex components. And matrices. So A usually, so A is a now it's a collection of numbers. First index gives you number of the row. Second index, number of the column, and so on. So we usually, so it's matrix in this case is 2 by 3, right? So it's 2 by 3. In general, it's m by n. So m rows and columns. So it also, we consider either real components or complex components. Elements. So vectors, matrices. Sometimes you just write the short version of the matrix Aij. It means that the elements are called lowercase a, and indices are Ij. So this is a way how you can write. So now there are different operations with the matrices. So the first is transpose. Transpose is when you flip indices. So A transposed is a matrix where you just, instead of Ij, take Ji. So it's a matrix where rows become columns. So now it will become 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. So this is a transpose, and then we also have a Hermitian transpose. So Hermitian transpose is used for complex matrices. So it's AH. So what you do the same flip of the indices, but also take complex conjugation. That's all different. So Hermitian transpose is transposed plus complex conjugation. So the properties, we know that if you take a product R, forgot to write no. The next operation is a product. So product of matrices. So we can take a product of two matrices A and B. So take product of matrix A, which will be m by n, times B, which is n by p. So when you take a product, the adjacent dimensions should be the same. So it's only way how we make a product. And then you get a matrix with the dimensions without a dimension. So it will be m by p. So its coefficients is, its elements is Cij. So element Cij is you obtain by taking a product of A elements and B elements, where you sum over the adjacent indices. So this is how you take a product, if you remember. So then, okay, so this product, then what's next? Inverse. Inverse of A is the A minus 1, so it's a matrix A minus 1 such that A minus 1A is same as A minus 1 is identity where I is identity matrix. So identity matrix is a matrix which has only the unity in diagonal on the diagonal, 0 otherwise. So identity matrix is when you multiply it to any matrix by I, it doesn't change. Okay, so we have properties. So the inverse matrix exists if and only if I double F is usually what's called if and only if. If and only if its determinant is non-zero, so it's other way to write what is that A minus 1 exists. Determinant, you hope you remember. And also there are a combination of these properties. So for example, if you want to take a product and take transpose, it's a product on transposes taken in inverse order. Same with Hermitian. And same with an inverse. So inverse of A, so A, it should be n by n, so it should be square matrix. So inverse only exists for square matrices. So it will be AB, and then it will be B minus 1, A minus 1. So what else? Next, for a square matrix A, we can define the concept of eigenvalues, eigenvectors. So this is will be widely used. So it's real or complex. So matrix can be real or complex, but eigenvalues, eigenvectors are in general complex in both cases. So they can be real, but in general they are complex also for real matrices. So it's eigenvalue and eigenvector is the solution of this equation, AU equal lambda U. So where lambda in general complex is an eigenvalue, and U in general complex vector is an eigenvector. So this gives a spectrum. So this is very important property, and we know that this equation implies so its solution exists if the if only so U should be non-zero. it's not zero vector. So its solution exists if and only if determinant of this lambda minus a minus lambda I is zero. So this is what's called characteristic equation. So this is how you know that lambda may be complex, because determinant is a polynomial with respect to coefficient. So determinant is a polynomial with respect to lambda. And even if A is real, the polynomial can have complex roots. So there are n complex roots which give you n eigenvalues. And for all distinct eigenvalues, you can define eigenvectors. So this is how it works. You can define a spectral radius. So these are just basic things I will define it, but then as long as we will use them, I will recall you what it is. So it's good to refresh it from the beginning. So spectral radius of a matrix is just maximum of absolute values of the eigenvalues. So maximum absolute value of the eigenvalue is a spectral radius. Also important thing. Okay, the next is so the n by n matrix, so square matrix is symmetric if it doesn't change under transposition. So changing indices, we get the same. And the same thing is, so n by n matrix is Hermitian. So if Hermitian transpose doesn't change the matrix. So essentially, symmetry can be defined both for complex and real matrices, but usually it's used for real matrices. And whenever you have a complex matrix, usually you use a Hermitian property. So, so usually this is for real matrix. And this is for complex matrix. Though sometimes symmetry is used also for real matrices, for complex matrices. But whenever this is for real, this is for complex, in both cases, all eigenvalues are real. So that's important. So all eigenvalues are real in both cases. So this is a property. And the next is so real symmetric. Or complex Hermitian matrix is positive definite if for real symmetric matrix is xtxa. So you see, this is a vector column, this is matrix, this is vector row. So this given number. So it's bigger than 0 for all non-zero real vectors. And in the case of complex Hermitian or Hermitian product, So this is what's called quadratic form. So it's a quadratic form with respect to components of A, of X. So its real form, quadratic form, is complex. So it's bigger than 0 for all non-zero complex vectors. So now real symmetric and all complex Hermitian matrices, they can also be positive definite. And in this case, all eigenvalues. So remember, they're all real. So in this case, all of them are positive. So these are very important situations. Well, all quantum mechanics is based on these properties. So next point is a norm. Norms. So norms first, let's start. Let's just consider Rn. Yeah, so that's essentially, Rn or complex or real vectors. Doesn't matter. Complex or real vectors. So there are many norms. So usually you can put norm which you use in the subscript. So L infinity norm is just maximum. So it's maximum component, maximum absolute value of the component. All right, so it's L infinity norm. And then we have usually the Euclidean norm. It's just, usually we write it just norm. Right? So it's usually this means x2, and this is square root of the sum of squares. So it's just usual distance in Euclidean space. So it's Euclidean norm. And then you can generalize it to LP norm. Yes, you take a sum of p powers of components and then root of order p. So this is LP norm. So there are plenty of norms that you can consider. And also you can consider the inner product or scalar product. So the two vectors, the inner product is a sum of all components for the product of xi by yi complex conjugate. So in the real case, so this is for complex case, and in the real case, it's just product. Remember, you know? So this is very, very standard. So let's. Standard for you to remember is what is a matrix norm. So matrix norm is for any vector norm, so for any norm which is with this beta is whatever we had before. So I will not write any index. you can just use any norm. So we can define the corresponding matrix norm. Which is associated with this norm. So that for any norm, so the analogous norm of the matrix will be sup x non-zero. Actually, it's max, but it doesn't matter. So what it is? It's a norm of the action of the matrix divided by the vector, norm of the vector. So how much, in a sense, what is the maximum amplification of any non-zero vector by the matrix? So it gives it's a norm, and of course it will depend on what norm you choose in the vector. So whatever norm you choose for the vector, you get corresponding norm for the matrix. So this gives you, in particular, all these kind of norms. So you can have infinity, you can have A2 or AP. So all these norms which correspond to the to different vectors norms, and there are different form of norms which are not related to the vectors norms, but just given directly, which are also useful. So Frobenius norm, or sometimes called Euclidean. To put E for Euclidean, it's just taking norm as you do it for the vector. So it's a square root of a sum over all components of squares. Just if you take all elements of the matrix, put them in one line, and take Euclidean norm of this vector. So this is usually called Frobenius norm. Okay, so that's it. So now we will walk. So essentially our goal of numerical linear algebra is to do all the operations in a numerical way. So to have an algorithmic way how you can solve different equations or find eigenvalues, find eigenvectors, so how to do it numerically. And so there are algorithms. So we start with something which is, so the most basic is solving linear systems. So we want to solve a linear system which is AX equal B. So A will be n by n matrix, right? X is let's take everything real. So A is real n by n square. So X will be a real vector with n components. B is a vector with n components. So given A and B, find X. So this is a problem. So this is linear system of equations. And okay, so we can write it just once in component form for you to remember what is this product. So just a way how remember the A has components A11 and so on. So the component, if we write it in component form, it will be A11 plus A12 x2, right? Yeah. A1. that system that we have, that we need to solve. Okay, so we already discussed this, so I will not repeat what we discussed. So we discussed two things. So Gaussian elimination. Gauss elimination. And we also discussed LU decomposition, lower, upper triangular form decomposition. So this was first lecture. And this was also first lecture. So essentially, the idea of Gauss elimination, remember that was just choosing one non-zero coefficient and by eliminate by taking linear compositions all the first terms in the other equations, and then do the same with the next one, then the next one, and the next one, so until you get to the upper triangular form, and the upper triangular form you solve it by backward substitution. And LU decomposition is something similar. Its LU decomposition is that you can is a method how you can write the matrix as a product of lower or upper triangular matrices. So L is a lower triangle, so it's only has components here, and upper triangle has only components from diagonal up. So now if you want to solve AX equal B, it means that you want to solve LU X equal B. You call UX as Y. So as a result, you get a system. You get a system of equations. So first you solve Ly equal B, and then you solve Ux equal Y. And here, first system is lower triangle, second system is upper triangle. So they both are solved explicitly by back substitution. So starting from the beginning or starting from the end, depending on the lower or upper triangle form. So this is how it works. So take a look at the first lecture, or even better read the book to remember what it is. I will just give you some application of this LU decomposition in case of positive definite matrices. So for symmetric positive definite matrix A. So what you have is the theorem is that the symmetric positive definite matrix can be written as LLT. So in that case, you see the upper triangular matrix is just transposition of the lower triangular matrix, where so symmetric positive, where L is lower triangular with positive diagonal elements. So that's a restriction. So that's some generalization of LU decomposition in this special case. So usually symmetric or Hermitian case and even symmetric or Hermitian positive definite matrices, they are much better behaved than general matrices. So this is a particular example. So you see the LU decomposition become just LLT. So you don't need U. So you can find L such that it already gives you complete decomposition. Okay, so I will not prove it. So this is not numerical linear algebra. This is linear algebra, rather. So just take a look. Read the book. You can take a look on in the book how it can be proved. So the next step, what we will do, are the three diagonal matrices, three diagonal matrices. Well, the name already speaks for itself. So it's a matrix. So it's n by n matrix, so square matrix. Where everything is 0 except on the three diagonals. So the main diagonal has elements A1, A2, A3, until AN. So it's n by n. And then there are one diagonal up, above and one diagonal below. So this C, no? C1, C2, and so on. And diagonal below will be B. B1, B2, and until Cn minus 1, and until Bn. And the rest is 0. So there are three diagonals. And this is three diagonal matrix. So very often you may encounter the three diagonal matrix in applications, and especially in numerical analysis. So what it means, it usually has to do with some chain relation. So because what it means is that whenever you write equation AX equal B, so for each equation, it means that this equation gives you a relation between the X component corresponding to this equation and two neighbors. Neighbors on the left, neighbors on the right. So this is the meaning of three diagonal matrices. So each equation is an equation between three adjacent numbers. We will see this, for example, will appear if you make a finite difference scheme for partial differential equations. So this is exactly three diagonal matrices appear for some of the schemes, and you need to solve them. So I will show you how it's done. Well, usually, I think that you will not remember it, but it's important to remember that there is a good method for three diagonal matrices. So that's a message. So whenever you encounter such a matrix, remember that there is a good numerical method. So these are matrices which are easier to solve, and then you may recall how it's done. But solution is essentially is direct. So we will suppose the form of the solution, and then just we'll see that it works, and when it works. Suppose that A has a LU decomposition of very specific form. So L is a lower triangular. So we have on diagonal alpha. And then below we keep the same b that was before. And this just has 2 diagonals, nothing more, nothing else. And so this is L. So U should be upper diagonal, so we will put unity, it's a unit on the diagonal. So it should be 0 here because it's upper triangular. And then we will put numbers that we will find, gamma 1, gamma 2, gamma n minus 1, and 0 here. So this will be U. So compute a product and compare with A. So how you do it? So for example, compute the product of the element 1, 1. It will be this vector, which is just 1, 0, 0, 0, by this row, which is alpha 1, 0, 0, 0. So product is 1, is alpha 1. So it means that alpha 1 equal A1. So this is the first what you can find. The next is you can multiply this vector by this row. Right, so it will be gamma 1 by alpha 1. And it will be equal to C1. The other products will give 0. So this means that gamma 1, C1 over alpha 1. So we found alpha 1, gamma 1. So the next step, of course, if you can divide, so if it's not 0. So then we can do it the same for these 2 elements, for these 2 elements, for these 2 elements. So the in general form will be that alpha I, you find it as AI minus BI gamma I minus 1. And gamma I, in this similar fashion, you will find CI divided by alpha I with the I 2, 3, so on. So it works if all alpha I are not 0. So you see, alpha I, all alphas, they stay in the denominator. So if they all not 0, it works. And it means that indeed you can make a decomposition. And whenever you make a decomposition, you can solve it. And you remember how we solve it. So we solve it through a system of 2 equations. So exactly this system. So AX, we will write F for not, because B we already used. So A is LU, which means that we have to solve 2 equations. Ly equal F and Ux equal Y. And we have L is very simple. So we can just directly solve the first equation. So you see, so for the first equation, for example, it will be alpha 1 by y1 equal f1. So we find y1. And then second equation, by back substitution, you find all the rest. So yi is fi minus bi, so just check it. So by back substitution, so you substitute back the previous one. divided by alpha I. So this is 2, 3, and so on. So you find all components of the first equation. And then having the y, you put it on the right-hand side and find x by back substitution with the second matrix. So it's essentially, so what is the first will be. But now you start with the last one. Right? So you multiply the vector by the last, you get xn. xn equal yn. So this is the first. And then you make back substitution, but backwards from n minus 1, n minus 2, and so on. So essentially, you can check that the solution will be xj is yj minus gamma j xj plus 1. So now xj plus 1 we already have because we're making back substitution. We go every time to the smaller index. And then j is n minus 1, n minus 2, until you get to 1. So this is explicit solution. So free diagonal matrices, they can be solved. So whenever you get them, you solve algorithmically with the only problem that we need to be sure that all coefficients are non-zero. And you can have one theorem that make sure that it works. So let's make a small interval. So interval break till 220. Okay, so there are simple conditions where it works. So let's just put, so you see, this is all wrong. So B star 2, 3, so it's index, it gives you index of the row. So it's B2, and this is correct here. So there is no B1. So remember, there is B1. So B1 is somehow out. So let's say that B1 is 0. B1 is 0. So there is a theorem that you can prove, which tells you that if all non-diagonal elements are non-zero, and so you see that B1 is 0, we take, and also there is no Cn, right? So let's say that Cn is also 0. Right? So that's, there is missing, it falls out. So Cn is 0. So all of them no good. No good. Forget about this. I thought I can optimize the formulation, but it's not really true. So if we have a collection of conditions. So for the first component, for the first row, we only have A, right? So we take A1 should be bigger than C1, bigger than 0. For the second, for all other rows, except for the last, we have AI should be bigger than BI plus CI. And BI, CI should be non-zero. And for the last row is A1, AN should be bigger than BN, bigger than 0. So essentially, what the condition means that diagonal dominates. So diagonal is bigger than the sum of the neighbors. So diagonal is stronger by absolute value, and also that there is no empty places on the out of diagonal of the first and third diagonals. So there are no zeros. So then, so this is for I from 2 to n minus 1, right? So then all alpha I are non-zero. That means that method works. So that's a simple condition that just verifies that everything works. The other way is just to compute and see that all of them are non-zero. Probably, I don't know what is easier. But so I will not prove it. So for the proof, you can see the book. I will try not to give very technical proofs in this course, because anyway we're talking about numerical analysis. So I will try to concentrate on proofs which are conceptual. So this proof is just technical manipulation of the numbers, just to verify that all alphas are non-zero directly. So we better do something better. So this is a three-diagonal matrix. At the same time, what is often appears is not just free diagonal, it's kind of free diagonal matrix, but where the diagonals are not elements, but blocks. So block three diagonal matrix. So it will be nm times nm. Nm times nm. So A is, so it's just the same, but now these will be blocks. This will be not just not just numbers. So it will be new matrices. E1, C1, A2, B2, C2, B3, C3, E3, C3, and so on until AN, Cn minus 1, Bn. 0, 0. So just similar to the free diagonal, but now all of them, so all of these free diagonal components are matrices. So this is just more general form of the free diagonal matrix, also very typical for applications. And it's good for you to know that this also can be solved in a very optimal way, just directly by LU decomposition. So what you do, so algorithm is similar. So take LU decomposition, already guessing the right form, and it will be the same decomposition as here, but now these should be matrices, right? So not numbers. So instead of alpha, we'll put A hat, 1, and instead of, then it's the same B. B2, A2 hat, 0, N hat, 0, 0. So this is L, and it's kind of L because it's not left upper triagonal, it's left upper block triagonal, right? So it's blocks. So it's diagonal formed of blocks, and the analog of U will be what is written here. Instead of 1, we should put unit matrix. So M by M unit matrix. Instead of gamma, we put E1. Until just the same as what we did here, you can just compute the product and compare it with the form of the matrix A, and then you find all components. So computing the product and comparing with A. So what you have is alpha 1 equal A1. In the same way, it will be A1 hat equal A1. And now this will be E1, A1 hat equals C1. So you cannot divide it by alpha. You should write invert the matrix, right? So it will be just in A hat times gamma. So there will be, so what you find is E1 is A1 hat inverse by C1. And then for the rest, so then the second row will be that all others will be obtained as just the same expression. That's E2. So here we need, assuming that all I are invertible. So this has become analog of assuming all coefficients here alpha I are non-negative. So here we need them to be invertible. So it's analog of what's negative. And then you do the same thing. So AX equal B. So if we call this L and this is U, you write it as system of two equations. But now X is just written like vector, and Y is, and so on. The B is also written like vector, and Y is as well. But now all of them, all coefficients, all components are not numbers, are now they're vectors, m-dimensional vectors. So it's a decomposition of vector in agreement with the decomposition of block structure of the matrix. And then you find the solution explicitly like we did there on the first, what you get at three diagonal matrices. So solving the first, you get, so again, so what will be the difference will be that you will not divide anymore, but you will use inverse matrix. And actually, we even do not write inverse matrix, we will keep alpha on the left-hand side, which will become A hat. So it will be, the first equation will be A1 hat Y1 equal B1, and the rest is AI hat YI equal BI, Y. So this was a forward-back substitution, which you solve. So at each point you have to solve equation or linear system for this A matrices, but this is much smaller system than the big one, right? So usually this method applied when the blocks are small, but the matrix is huge. So for example, when you solve numerically partial differential equations, then matrix is probably how many variables you have. It's like 3 by 3, and number of the blocks is million. So then, of course, this is cheap to solve. When if you just solve it directly without knowing that it's three diagonal, it will be very expensive. And then the second system, you do it backward substitution, so it's also, so this is explicit. Here you don't need to solve anything. Okay, so this also works. Okay. So that's how this linear system of equations are usually solved. So you normally use LU decomposition. And in some cases, LU decomposition become simpler. Like for symmetric matrices, or the diagonal matrices and so on. So LU decomposition can be used to make it even better. Okay. So the last topic for today will be error analysis. So we already started it on the first lecture, I guess. It was about the condition number. Let's repeat it, but slightly. Well, I think this should be repeated several times because this is what you have to remember. So the condition number is a very important property. And we introduce it for matrices, but in principle it has other generalization. What is it about? So let's assume that we have exact system to solve. So we have exact system, AX equal B, and we find X. So this is ideal situation that we want to have. But in reality, this doesn't happen always. So usually we don't have B exactly, we don't have A exactly. So we have an error in X. So now we want to know how big is an error in X depending on errors of the input data. So you have input B, input A, but with some errors that you can have some idea of how big they are. So you know how big will be the error of your solution. In this case, just assuming that all calculations are exact. So you do all calculations exact, and just so how to find the error of solution as an estimate error of solution, knowing what were the errors on the input. So errors of input data. So errors of input data, it means that you don't have A, but actually what you receive is A plus delta A. So there is an error, there is some perturbation. And instead of B, you receive B plus delta B. And so it means that you solve, in reality, this equation. So you find an error of the solution. So it's solution with error. So whenever you have perturbation of matrix, perturbation of vectors, so of course the solution will also be perturbed. So we will denote change of the solution by delta x. So we want to express delta x in terms of delta A, delta B. So theorem. Now, first, let's put definition. So given a vector norm, we define a corresponding condition number given the vector norm and invertible matrix A. So invertible means it's square. We define square and determine non-zero. So we define the condition number. So the as cap of A. So it depends on a norm, right? So for different norms, it's different definition. And it's just norm of A, or so the induced norm of a matrix by norm of the inverse. So you see, if you remove this central part, this will be A by A minus 1 is identity. Norm is 1, right? So, the condition number is how much changes if you split this part. And we will see that it has to do directly with the computation of the error. So theorem. Theorem tells you that solution of this equation, for the solution of this equation, is the relative error of the solution is bounded by condition number divided by, no. Assuming that delta A minus 1 is smaller than 1, we have, so there is some condition which assume that perturbation, this inverse matrix, we assume that the perturbation is not too large. So usually if it's small, then it's, if the error is small, this is true. So this is just condition that error is not tremendously large. We have estimate on the relative error of the solution. So it's small or equal. So the first coefficient is a condition number divided by 1 minus this part, so which is smaller than 1. So it doesn't cause a problem. Usually, if the error of the matrix is very small, so this is close to 1. So the denominator is not so crucial. So this condition number is important. And then it's multiplied by the sum of the relative errors of the input. Relative error of the right-hand side plus relative error of the matrix. So this is a theorem. So in particular, we can find the formula that we already had on the first lecture, or second, I don't remember. So for example, if matrix is exact, but we only have an error of the right-hand side, so denominator is 0, this is 0, so then we get so that the relative error of the solution is bounded by condition number by the relative error of the right-hand side. So this is already exactly what we had. So this is a condition number is amplification factor. Amplification factor of error, of relative error. See, so whenever your right-hand side is given with a certain error, this error will be amplified in the solution this number of times. It means, though, that the matrix is ill-conditioned if condition number is much bigger than 1. So if condition number is very, very large, it means that even if you put small error as an input, you will get much larger error as an output. And sometimes, in some cases, this number can be tremendously large, like millions or more. So if this happens, it's a problem because small error can lead you to the results that make no sense. So that's why this condition number is important. It's easy to compute. You see, so I mean, that at least formula is simple. So let's prove it. Proof. Okay, so how you do the proof? You open this product. Remember that AX equal B, so AX equal B cancels. So what will be left is the rest. So what will be left from this equation will be A plus delta A by delta X. And then there will be also delta AX, which we'll put on the right-hand side. So it will be delta B minus delta AX. So this is a result from this equation where we subtract the exact system. So then we can use the property that if A is invertible and we have this condition, this one, the one matrix norm by another matrix inverse norm is more than 1, then the sum of the matrices is still invertible. So it's C, linear algebra. So it's also in the book. I remember I had it in the course of linear algebra when I was giving, or in exam even. So that's a standard thing that you can see in linear algebra. So just try you can prove it by yourself. So it's good exercise. So it means that what it means that this condition that I put in the theorem, it allows us to solve it. So there is a solution. Okay, so let's write a solution. So what we will write as a solution, so we'll write A minus delta A as A times identity minus A minus Y delta A, and then invert it and put it on the right-hand side. And this gives us delta X. And when you invert, you change the sequence, right? So it's first the last. Okay, now we take norm from both sides. So now this is vector, this is matrix, so we can take norm from each of them, and this will be inequality, remember? Because this is by definition of what is the norm of the matrix. So this will be inequality. And here the norm, we take triangle inequality, so it's delta B plus norm from this, delta A x. And then what we do is we use from linear algebra, so check that this is smaller or equal than 1 over 1 minus norm of A minus 1 norm of delta A. Exactly that, this term. So just some exercise of linear algebra can give you this, so check it. And the next, remember that from x, remember that since ax equal b, that it means that then in the norm form, this will be bigger or equal than b, right? Which means that x is bigger or equal than b over a. Huh? Yeah, that's true. Or not? No. Not here. That's okay. That's fine. That's fine. So we keep this. Well, let's go slowly. Just let's write it as it is. So now what we do, we multiply it here by norm of A, and here we divide by norm of A, right? So this will be condition number. And also let's divide it by x. So it will be delta x norm divided by norm of x. So, and this will be, he will have a and x to divide. And here we'll just have delta a, x cancels. Okay? So what remains to see is that, remember that ax equal b. So a in the norm form, it's inequality. So this is bigger than b. This is smaller than equal. And this is in denominator. So this is bigger than, then it's smaller than, so then putting them together, you get exactly what you had. in the theorem. So put this into here, and then you get the result. So essentially, that's it. So the condition number is important property. You can compute it directly through two norms, and it gives you how much error will depend on the error of the initial condition and of the matrix, and essentially the message that both errors will be multiplied by this factor, which is condition number. There is still denominator, but this denominator, for small errors, it's not important, because this is essentially 1. So what is important is kappa. And I give you a few properties to remember. So properties of the condition number. So the first property is that condition number cannot be smaller than 1. Big or equal than 1. This is kind of simple, because so see the kappa of A by definition is what? It's A minus 1A. But that's a norm. So so you can, the norm of the matrix has a property that is bigger or equal than the norm of the product. This is for any matrix. Because this is maximum amplification of a vector, and this is also maximum amplification. And this is just product, direct action of the linear operator. Okay, and this is identity. So this is 1. So it cannot be smaller than 1. And the next good thing is that when it is 1. So what is the B? So the matrix is perfectly conditioned if condition number is 1. So it's the smallest possible, so it's the best matrix in terms of the amplification of error. So if condition number is 1, we know that the error will not be amplified, almost, except for this denominator, which is become 1 for small errors. So when it happens, it happens for orthogonal. So it's in case of real or unitary, in case of complex matrices E. So what means orthogonal? It means that A transpose A is identity. So it means that inverse coincides with identity, or with transposed. And unitary means that AH, A equal identity. So it's Hermitian transpose coincides with the inverse. This is orthogonal means of the meaning of orthogonal matrices is that orthogonal matrix essentially is rotation or reflection. So in that case it's rotation, reflection. And in that case, it's logical that if it's rotation and reflection, that whenever you have to rotate the vector in order by this matrix in order to get B. So it means that if the B has certain arrow, that this arrow in X will be the same as arrow in B, because you don't stretch anything. So you just rotate. So whenever arrow was in B, by back rotation, it will be arrow in X. So it means that in this case, kappa 2 of A is 1, which means so for usual Euclidean norm. So this is rotation with respect to Euclidean norm, so it's isometry. And so when you compute condition number with respect to that norm, it's 1. So that's an example. So that's why essentially the orthogonal matrices are very nice for computation because they do not amplify errors. So you don't worry about errors if it's orthogonal or unitary. Okay, good. So I think we're done very precisely. So see you. Thank you. See you.